Hello everyone, and welcome to session 5 of this series where we will use the structural analysis program Ftool to analyze the statically indeterminate beam with a fixed support and two roller supports shown in the figure on screen. I will first briefly go through the hand solution of the beam using the consistent deformation method and either the moment area method or the conjugate beam method. Then I will perform the steps required to solve the problem using the computer program. I will ask the program to draw the shear force and bending moment diagrams, as well as the deflected shape of the beam. The problem uses the standard international system of units. The modulus of elasticity and the moment of inertia of the beam are not given in numerical values, as they will cancel out in the hand solution because the beam is not subjected to any support displacements. Yet numerical values will have to be inserted into the computer program in order to solve the problem. The magnitudes on the deflected shape will depend on these numerical values assigned. As you can see from the figure, the beam is statically indeterminate to the second degree. The primary and secondary structures are simplest when the support reactions RB and RC are selected as redundants. On the primary structure, the deflected shape will be a curve from point A till the point where the load is acting, followed by a straight inclined line from the point where the load is acting till point C. On the secondary number 1 structure, the deflected shape will be a curve from point A till point B, followed by a straight inclined line from point B till point C to satisfy compatibility of deformations. Remember when we defined the principles of structural analysis as linear elastic, which represents the material behavior, in addition to equilibrium, and then compatibility, where compatibility here means no breakage or gaps are present in the structure. The linear flexibility coefficient, FCB, on the secondary number 1 structure can be obtained by adding to FBB the product of the angle of rotation at B, which is theta B, times the distance from B to C, which is 6 meters. On the secondary structure number 2, the deflected shape is a curve throughout the beam, as the load is acting at the tip of the cantilever at C. The moment area method or the conjugate beam method are very much suitable methods for solving this problem. By setting up the compatibility equations at B and C, using the deflections and the linear flexibility coefficients that we calculated above, we can obtain the required support reactions. Let's now proceed to the computer program solution. Start your Ftool program and open the metric template that we created in previous sessions. If you did not watch that, please go back to previous sessions and watch these sessions in order to keep up. Many of the steps that should be performed here I have already created in previous videos, so I'm just going to skip not to waste your time. You can refer to previous sessions to check the full details. After you have opened your metric template, we're going to start by creating our nodes. I'm going to activate the keyboard mode and click on Insert Node. The first node would be at 0, 0, then at 5 meters, 8 meters, and 11 meters. If you can't see all nodes on the screen, then just click on Fit World on screen. Let's create our beam segments differently this time. Keep the keyboard mode on and click here on Insert Member. You can either use the absolute setup where you will have to insert the node coordinates at node A and node B for each segment, or you can use the incremental setting, which is easier. For example, we can tell him the first node is at 0, 0, and I want the increment to be 5 meters in the X direction, and then click OK to create the first segment. And then I want the increment of length to be 3 meters, and I want you to create 2 increments. So I'm going to click OK once and then twice. As I have shown you in previous sessions, there are many ways to create your nodes and beam segments. So I'm trying to alternate between these methods in different sessions. I'm going to click Cancel. And now we are ready to add our material properties and cross-sectional properties. I have already opened my metric template, so I have some standard international system of unit values already assigned here. I'm just going to select all of my beam segments and click Assign. And I also have some predefined values for the moment of inertia. And I am introducing again a very large value for the cross-sectional area in order to eliminate axial deformations. I'm going to select all of my beam segments and click on Assign. Next, we want to define our supports. We have a fixed support at the left side of the beam, and then we have 2 rollers. We're going to start with the fixed support. For the fixed support, we're going to have restraint applied to the X, Y, and rotation. I'm going to add an angle here of 270 just to make the fixed support look right on screen. So here's your fixed support. Then I'm going to choose this node. Press down on Shift and choose the other node here because both of them are rollers. The setup for roller, we have only a reaction in the Y direction, and I'm going to fix the angle here and click Apply to have the 2 roller supports. Now, in order to add our load, we will have to press here on Nodal Forces. Again, if you would like to know how to create a new load, being distributed or concentrated, you can refer to the previous sessions. I don't want to repeat that in order not to waste any of your precious time. So I'm going to go to the next step here, assign the node where the load is acting, and click on Apply. So the setup is complete. We have defined our nodes, our beam segments, our support conditions, our material properties, and cross-sectional properties, and we have defined our loads. The next step is to go to the axial force diagram. We don't have any axial forces here because we have eliminated the effect of axial force by increasing the cross-sectional area to a very large number, but I like to press this one here and on display click on reaction values in order to see the reactions that the program calculated. We can compare these two reactions, 32.9, 15.3, to the values obtained through the hand solution, where you can see that they are identical with some differences, minor differences due to approximations in the hand solution process. The next step is to remove the reactions. You can also remove the supports to have a clearer shear force and bending moment diagram. I'm going to click here on the shear force diagram, and then on the bending moment diagram. And finally, we can click here on the deflected shape diagram. I'm not going to show any values here because the problem did not give us a specific value for the modulus of elasticity or the moment of inertia. So the values here will pertain specifically to the values that we have introduced here at the beginning of this problem. But for now, we're just interested in seeing the shape or the orientation of the deflected shape. The values will depend very much on the properties that you introduce, whether material or cross-sectional properties. There we go. Thank you very much again for being with me in this session, and I hope that I will see you in the upcoming sessions. Best wishes.